it is my pleasure to welcome Dave Storkey today. So Dave has been working on some aspects of spin-up of the ocean and accelerating that with NEMO. There was a deliverable in December, and he's going to tell us about that and any progress since. Over to you, Dave.
Okay, thanks, Malcolm. Hello, everyone. So I'm going to talk about trying to accelerate the spin-up of climate models using NEMO. So just to give a little bit of background to start with. So as we all know, there are processes in the climate system which take a very long time to adjust, and that's a problem if we want to initialize climate simulations from a sort of equilibrated state. Some processes can take thousands of years to spin up, especially the deep ocean and the carbon cycle on land surface. And so there's quite a lot of interest at the moment in various techniques to try to accelerate the spin-up process and try and reduce computational load. What I've been working with Samuel Katawala, who was at Oxford, is now in Tokyo. And he's published a couple of papers recently about applying something called sequence acceleration to the spin-up problem, and in particular to try to speed up the spin-up of the biogeochemical models in the context of a system modeling. So sequence acceleration, just to give you a sort of overview of the approach. So it starts by thinking about the spin-up problem as a mathematical convergent problem, and so you can write it as a convergence problem, so as a sequence. So x of k plus 1 is g of x of k, where g is basically a mathematical. It's just a mathematical representation of the numerical model, and you just spin this up until x of k plus 1 equals g of x of k, right? That's your convergence criterion. And then the nice thing about that is that if you think about it as a sort of mathematical problem, there are mathematical techniques that have been around for quite a long time for accelerating convergence, accelerating the convergence of convergent sequences. And so the one that Samar had to play with is called Anderson acceleration. And it is basically a sort of a sophisticated type of extrapolation, I guess. What you do is you, instead of you basically say that the next model state x at k plus 1 is a linear combination of a bunch of the model applied to a bunch of previous model states, maybe 50 model states, and you determine the alphas in the linear combination using a minimization problem. And then the nice thing about this is that it's completely separate to the model. So the model is this G, but in order to do this minimization problem, all you need is your 50 model states, right? And then you can update the model state, and then you run the model on from that. So in principle, it's quite a nice thing to do because you can treat the model as a black box. So Samar has published a couple of papers showing that he got something like 10 times spin up of the biogeochemistry models. And so the idea now is to see if we can apply the same technique to the physics, in particular deep ocean spin up. So Samar, this is unpublished work, but Samar has demonstrated a 5 times spin up of the trace fields in MRT-GCM with about a 1 degree ocean configuration. And so what I've been doing is the first thing I've been trying to do is replicate Samuel's result using NEMO. So using NEMO in Orca 1, which is a roughly 1 degree global configuration of NEMO. And then the idea is if I can get that to work, is to go on and see if we can get this to work with an eddying ocean, so with Orca 85 to start with. So that's the sort of background, that's the goal. So that's sort of the experimental design. So this schematic is from this paper Yule et al. So it's documenting the spin-off of the UK ESN model. And it had a very complicated spin-up procedure where they ran various parts of the ESN model separately and then put them all together and do more spin-up. And the bit that I'm interested in is this kind of ocean-only bit that they did to start with. So they ran for nearly 5,000 years ocean-only to try to get the ocean biogeochemistry to spin up in particular. And so that's what I'm focusing on, kind of ocean-only forced experiments. What Yule et al. Did for that part of the spin-up was to take for atmospheric forcing field from a previous PI control run, and in their case they took 30 years of atmospheric forcing fields, and then just spun the ocean up, repeating this 30 years over and over. In the context of biogeochemical spin-up, Samal found that his acceleration technique didn't really work with that, and I'll come back to this. Didn't really work with intranic forcing, so he found that he had to use repeat year forcing because there was less variability. But what he shows in his paper is that you can do that. You can use his acceleration technique with repeat year forcing, and then get that spun up, and then use that to initialize an integration with intranic forcing. And overall, you still see an acceleration. And so that's what I'm trying to do. I'm trying to sort of replicate what he managed to do with the repeat year forcing. And then if I can show that that works, then I can initialize an intranic forcing test. So that's context. So I'm using Walker 1. I have 2,000 years of control simulation I'm using 60 years. So with experience, they decided that 30 years was not quite long enough. So I'm using 60 years of atmospheric forcing from PI control. And then the control for the acceleration test is using a repeat year atmospheric forcing. So I've just taken one of those years from the 60 years. All runs use the same dot formula as in the coupled model. So you want to keep as close to the coupled model as we can. And as I said, the repeat year forcing that's the control for the acceleration test. So there's another complication. So Samal found that for the physics, if you just apply his acceleration technique to the model in a simple way, it doesn't work. It's unstable. And so he came up with this kind of trick to get it to work, which I'm calling passive tracer mode. And so what you do is you add an extra temperature field and an extra salinity field to the model, and you run the core NEMO model in the usual way, but the core model just repeats the same year over and over. But the passive tracer fields, they have the same equations applied to them, but they're allowed to evolve year on year. And doing this, he found that he could apply acceleration to the passive temperature and salinity field, and that works. And then every now and again, so the temperature and salinity fields are passive in the sense that they don't affect the density. But every now and after about 50 years of this, you recouple these passive fields to the density field, and then you run NEMO for a bit, just as a normal model, just to let the density field, let the velocity fields adjust, and then you repeat the procedure over and over again. And so, well, this is just a little bit of you have to do a bit of work in NEMO to implement this, but it's fairly simple because basically it's just a loop on the tracer equations. So you just apply the tracer equations once to the active temperature and salinity, and again to the passive temperature salinity. And there's a nice sanity check you can do if you initialize the active TNS and the passive TNS from the same field, and you get a big comparison at the end, so you know that you haven't screwed anything up too badly. So results. I perhaps should have warned you at the end. I don't have any positive results at the beginning, but I don't have any positive results yet. So on the left, I'm showing Samal's result that he got with MRT GCM. So what he's showing here, he's got a 3,000 year, the blue line is a 3,000 year control run. and he's showing the RMS difference of temperature with respect to the endpoint of the control run. So, not surprisingly, it converges to its own endpoint. But then the red line is the accelerated run with this passive tracer mode trick. And he's also shown this is RMS with respect to the endpoint of the control run. And you can see it's getting there faster, right? The curve's steeper. So that's kind of result I want. So on the right here, I'm showing what I've got at the moment. And this is without any acceleration at the moment. So I'm just using the passive tracer mode. But you can switch acceleration on and off, and I've just got the acceleration turned off at the moment. And you can see that, this is only 30 years, and you can see, so basically you want the passive tracer mode to follow the same trajectory, or a very similar trajectory as a control, otherwise there's no point, right? And you can see that it's diverging very quickly. So this is a problem. So the blue line's temperature, the solid line is control, and the dashed line is the passive tracer mode, and the orange line is temperature salinity. But I have a couple of ideas. I think one of the things that's going wrong here is I'm not allowing enough adjustment time. So these runs are starting from rest, and obviously if you start the ocean from rest, you get a very large adjustment to start with. I'm turning on passive tracer mode quite early in the run, and I think effectively what that means, what I'm showing here are annual mean trends in temperature just at 300 meters. At the beginning of the run, I've got the control on the right and passive tracer mode on the left, and then from 10 years into the run, and you can see the control run, you get this really big adjustment, which dies down very quickly. These trend plots are all plotted on the same scale. But of course, with the passive tracer mode, you're effectively forcing the passive tracer mode with these very large trends at the beginning of the run. So it's perhaps not surprising that they diverge. So one of the things I realized I need to do is start the passive tracer mode. I need to allow the control run to spin up for a while and then start the passive tracer mode. So this is starting at year 100 or 101. And I'm showing similar plots here, and you can see initially it looks a lot more promising. The various lines, the dashed lines are going roughly the same direction as the solid lines, but then when I run it for longer, it still diverges, so there's still a problem. So that's as far as I got so far, really. So the thing that I'm trying at the moment is to allow a longer adjustment period in between passive tracer mode cycles. So just to come back to this schematic, you allow the passive tracer mode to evolve for about 50 years, and then you reconnect it to the density field as an adjustment. And I've only allowed a year for that adjustment. It probably needs longer, so I'm going to experiment with using about 10 years or something like that. And there's another thing I've been talking to Samar about this stuff. There's another thing he does, which is to try a sanity check, of forcing the. So when you've got your control run completely converged, you can use those fields to force your passive tracer mode, and it should converge. And that's a nice sanity check that he applied. So I haven't tried doing that yet. So that's as much as I've got to say about the acceleration. I've just got a couple more plots, which I thought were quite interesting. So I've been having a little bit of a look at how the various spin-up runs evolve. So in particular, looking at the heat content of the ocean. So this is plotting the heat content of the ocean kind of globally, and also splitting it into two layers, top 1,000 meters and below 1,000 meters. And this is plotted as equivalent fluxes. So this is like the implied flux. So for a given heat content change, what will be the flux through the surface of the ocean that you need to get that heat content change? It's just an easier way of thinking about it. And so this is what you see when you use the repeat year PI control forcing. So this is what I'm using for my acceleration test, and you can see it kind of converges quite nicely. So after about 1,000 years, the total heat flux is about 0.05 watts per meter squared, and actually the top 1,000 meters gets down to roughly zero after about 500 years. And then after that, what's happening is the lower ocean, the deep ocean, is just carrying on taking a heat. So the surface flux is basically the heat that's going into the lower ocean. So that's quite nice. Then if you, this is what happens if you put repeat year forcing on. And so I think this kind of illustrates perhaps why the acceleration doesn't work very well with intraannual forcing, just because you have this massive variability. And I think, which is going to be difficult for this, if you don't have a nice smooth conversion, you can imagine this technique is probably not going to work very well. This is quite interesting. So if this is showing the same plots just with a running mean applied, 100-year running mean, and I've done this for 2,000 years, and it looks like we're getting kind of similar behaviour to what we get in the coupled run. So Jeff Ridley published a paper about this a couple of years ago that in the coupled run at low resolution, what you tend to see this pattern where the ocean takes up heat, the heat gets transferred to the Southern Ocean, and eventually you get this massive polynomial event which releases the heat, and you get this kind of cyclical behaviour. And it looks like, it's quite interesting, it looks like the same thing's happening in this force run with the PI control. So you get this big event after about, whatever it is, 1,500 years, where the heat flux at the top of the ocean goes negative, and you get the same, and this goes all the way down to the deep ocean. It's just releasing this heat, and then it goes positive again. So I thought that was quite interesting. And then just the last plot on Malcolm's latest EERIE LLPI spin up, and he's looking at the same thing. And yeah, so the mean here is quite close to zero. I think 0.05 watts meter squared or something. But you get this huge variability. But yeah, unsurprisingly, kind of damped for the deep ocean. So yeah, so that's what I had.
Thank you, Dave, very much. Very interesting. So, questions? Hopefully I'll be able to see hands, but if I don't spot you, then shout. I guess maybe I'll dive in with an initial one. So there's no reason to think that Samar's method working on the model MITGCM, that it's not specific somehow to that model, then there's no reason why it shouldn't work in any other particular model.
Nothing occurs to me.
Yeah.
I mean, it should fundamentally be quite a similar model. I mean, there will be differences, of course, but I don't see why it shouldn't.
Yeah. Okay. Right.
And it's a very similar configuration. It's the grid. The resolution is very similar.
Yeah. Yeah.
So.
Okay. Anyone?
Hey, I've got a question.
Yeah, go for it.
So this is Fraser here from MPI.
Hold a minute, Fraser. Let me try and up my volume so we can actually hear that well. Yeah. Oh no, sorry, that's the wrong one. Try this one. Yeah, go for it.
Yeah, I guess so. I think in Samar's when he was applying to MIT-GCM, he looked at kind of using this to speed up the acceleration of things like age tracers. Have you looked at or do you know if kind of that's been explored anymore in higher resolution models since then?
I'm not aware that he's tried it in high resolution models.
Okay, thank you.
Anyone else?
Well, maybe a follow-up question then. We saw that this method doesn't seem to like the extra variability you get when you run it with the kind of the interannual forcing. Do you think kind of the extra variability you get in an eddy resolving model might also pose issues for the method, or do you think that type of variability might be different, or is this something we could apply to maybe high resolution models, or yeah?
Yeah, that's definitely the idea. We definitely want to test it. We definitely want to have a go. I mean, I don't know is the short answer.
Okay.
I suppose one idea I had is perhaps because basically what's happening is in terms of large scale, the ocean's taking up a lot of heat, which is a bit unphysical, but that's what's happening. And perhaps that might dominate. So perhaps the acceleration might cope with it, but I really don't know.
Okay.
Anyone else? Anne-Marie?
Yes, thank you for the presentation. I wonder what in fact is the conclusion, because it's not possible to get rid of the interannual variability. So let's say if you try to spin up with repeated cycle forcing, when you switch on interannual variability, everything you have gained will be lost, won't it?
Well, so in one of his papers, Samuel showed that so in the context of biogeochemistry, he could do the acceleration with a repeat year forcing and then initialize an interannual forced run, and that overall he got accelerated. He could accelerate the thing overall. So he called it, I think he called it optimal initialization of the interannual run.
So the interannual run is just a normal model simulation. Is that the idea? You're not trying to accelerate.
No,
it's still
no. So you don't apply
the
acceleration to the interannual run.
Yeah.
So you do an accelerated repeat year forcing run, and you use that to initialize the interannual run, and then to get so for that in that context, they were looking at SCCO2 fluxes to get to whatever they were aiming for was quicker.
Right.
So the hope is that would apply to the physics, but obviously we don't know until we try it.
Thank you very much. Thank you, Dave. Great. So the other thing we're doing today is doing a brief catch up on how the phase 2 simulations are progressing. So let me try and share that with you. Oops. So I'm kind of going to whiz through a few slides, and then my colleagues will pick up their particular aspects. So some of this, well, the format was from the project review presentations that we gave on Thursday, which seemed to go very well with our project reviewer and EU project officer. So that looked very positive. They were very happy with our progress, so that's good. So yeah, so the phase 2 simulations. So to recap, so all the phase 1 simulations are complete, and if you're expecting some phase 1 data and you don't have it, then you should ask us where it is, as I know various colleagues are asking me where our data is, and I'm trying to provide it. So that's where we are. And then, yeah, I'll kind of work, because I think these have been presented, but just some of the things we presented at the project review with some plots from our Agile model, from capture made from ESMVAL tool of the multi-decadal trends, and some of the PCMDI metrics outputs. So for phase 2, so as you know, we in phase 1 ran 3 models with the high-res MIP experimental design. And the plan is for phase 2 to produce extra ensemble members for the period 1975 to 2030, using effectively the same model configuration. So we're having extra ensemble members for that time period, because from our various discussions, it seemed that would be the most useful way to use the HPC resources, rather than developing different models or doing a different experimental design or whatever, or starting indeed back from 1950 again. So that's what we're planning to provide. There might be some other extra simulations as well, but that's, I think, the key output from those 3 models. And then for the Met Office, we're planning to do some 7 fast-track simulations with the same science configuration of the HH model that we've used with EERIE, but with obviously the CMIP7 forcings. I'll say a little bit more about that in a minute. So this is the phase 2 from BSc. Pablo, did you want to say anything about your slide?
Yes, sure. So I can say we finished the historical simulations. So the new 2 members. We now have 3. You can see them in the plot on the top right. We also completed the future scenarios, but we realized that we got the problem with the forcing. We're repeating them now, and they are in year 2027. And the plan is to go beyond 2030, so to complete the full scenario period, reaching to 2050. And we are also going to run another ensemble with the SSP 370 forcing. So we have full comparability with the Destiny runs, which also have similar future scenarios. At least we could say something about whether the future responses are compatible. So that's on the 10-kilometer scale simulations. They're running fine. They could be finished in about 2 weeks, a little bit more. But then we'll need time to post-process them. That might take a little bit longer. We'll give priority to monthly outputs and to anything that is requested to us directly. And we also have completed a full, just one member, a full Aerosmith set with the 25-kilometer version. But we've been evaluating the AMOC, and it looks like this is not very good configuration. You can look at the bottom right figure, and yet the low-res version has this very rapid AMOC decline. It's completely unstable. Trying to investigate what's happening. And yeah, we don't recommend its use, given that this should be affecting the full climate system. We might redo everything, but that might take a little bit more time.
Great, thank you very much. So, Icon, Jürgen, did you want to say anything?
Yes. So we are in phase 2. We produce the 2 members in parallel, and currently we have a bit problems with the performance on the Levante, but if things go back to normal soon, we should be able to finish this within the historical runs, at least within 1 or 2 months, let's say. And the second line here is actually the issue here. We have we didn't get a lot of resources that we were asking for, and so the problem is we may be able to finish the 2 members, including the scenario runs, until 2030 only. Originally, we were also planning to do it until 2050, and we asked for resources for that, but we're very limited with the CPU time. And when I say resources, it also applies to storage. We're always at the limit with storage, but well, everybody knows this. This is, I think, a general problem, and I think for that you can always find solutions dealing with the tape archive in the back and so forth. But the CPU time, I hope we get CPU from somewhere else. And the other thing is to mention here is we have another chance to apply for some for the second half of this year. So I'm still optimistic that we will get some more, because there's, I think, more experiments on the list, and we would also like to extend it to 2050. And we haven't mentioned the time slice experiments yet. I don't know if they're off the table or not, but well, we certainly haven't started yet because we haven't designed them the way we wanted so far. I think that's it from our side.
Great, thank you very much. Rohit, do you want to talk about the AVI simulations?
Yeah, so
yeah,
regarding AVI simulations, so we have so the second ensemble members, so we are running in two machines, one in Jewels, one ensemble member completely in Jewels, and one in Levante. So the Jewels one is quite almost there. So we have completed the historical and scenario until 2020, and so far looks everything fine. And so we will finish, I think, within this month, this ensemble member. But with the Levante, we are around 2000, so we still 30 years to go. And as Jürgen already mentioned, that we have also computing resources limited, so we would try to finish this. We would be able to finish until 2030, but also in January we had a little issues in the Levante with how the performance is going. So we are also a little having some not so pace off, but hopefully in the next weeks we can pace off the simulation or find a way that it can go forward fast, so that in a month of time at least also the member 3 is also ready. So at least I will try to update the catalog from my side, so that at least one member that completed the historical and hopefully scenario in the next days can be added and everyone can access, and then eventually the third member also. Yeah.
Great, thank you very much. And then, yeah, just from the Met Office side, so as I mentioned, so our plan is to run our high resolution model for the fast track with CMIP7 with 3 historical and future members. We might try and do two, maybe at least 2 different scenario simulations. So this is enabled by us finally having access to our increased capacity supercomputer, but not yet the increased capacity data storage. So the data storage solution is going to be kind of rather ad hoc and is being developed over the next few weeks to be ready to start running these simulations early to mid next month. So the simulations themselves should finish kind of May, June for the historical, and the scenario kind of 1 or 2 months later. So the model runs about 2+ years today on the upgraded machine. So, but if you thought the data access for our EERIE simulation so far was difficult, then you haven't seen anything yet. So, but if you have particular ideas of papers to write, either for EERIE and or for CMIP7. So as you might know, the timescale for CMIP7 is that papers need to be submitted by March 2027, is my understanding. So given that I think no group have submitted any CMIP7 simulations so far, that is a very tight deadline. But if you really want to use this data, compare it to the EERIE runs or whatever as to wrap it into a CMIP7 paper, then please get in touch with us as soon as possible, because we're going to have to figure out how to deal with this temporary data storage solution, but also how to try and make the data available as well. And I'd say we're basically trying to think about solutions for the data kind of basically right now. So if there's anything that you would really like from those, then let us know and we can try and sort it out, because it would be really nice to have these 7 simulations and papers written up for the IPCC deadline using them. And that is all I have on our phase 2 simulations.